Hello friends, welcome to the course Essential of Data Science with R Software 1, in which we are going to understand the basic concepts related to the probability theory and statistical inference. So from this lecture we are going to start a discussion on a new topic, that is estimation of parameters. Now the first question comes, what is this estimation of parameters? Now if I ask you a very simple question, why are you trying to learn this data science? What is the basic objective? What you really want to achieve? So the answer is very simple. I want to know something, or I want to get an answer of some questions, queries on the basis of a sample of data. But the main problem is, I am trying to solve this problem on the basis of a sample of data, but what I want my conclusions to be valid, or they should remain valid for the entire population. Think about it. This is exactly what are you trying to do. For example, suppose you want to test the efficacy of a medicine. What we try to do? We try to take some number of people who have got the disease, and we try to give them the medicine. And based on their outcome, that how many people have responded that they are cured, they are not cured, etc., we try to make a conclusion. Have you ever heard that a medicine like paracetamol will control the fever of only Indian people? Or you have heard that this medicine will not work in, say, Germany, US, African countries, or anywhere in this world? No. Wherever and whenever any person in this world has a problem of simple body temperature, the persons are using the paracetamol and they are getting cured. But do you think that this experiment was conducted on all the people of all over the countries in this world? No. This experiment was conducted at some specified place by choosing some number of people, but the conclusion that this paracetamol is going to be effective for controlling the body temperature is going to be valid for the entire population, right? So my question is, how to achieve this, how to get it done? So essentially what are we trying to do? There is some characteristic which is for the entire population, and we want to know the answer of that question, or I want to find out the value that is valid for the population, but this is pretty difficult. So we try to do that, we try to take a small sample from the same population, and based on the sample we try to do our statistical calculations. But what we want, that whatever statistical calculations we have done on the basis of a small sample, they should remain valid for the entire population. So now how to get it done? How to ensure that whatever we are doing on the basis of a small sample will really remain valid over the entire population? Or for example, if I say that you want to know the population mean, that means the mean value of all the units in the entire population. But suppose you try to take a sample and try to compute the arithmetic mean, and you assume that this arithmetic mean is going to indicate the value of the mean which is in the population, not in the sample. So now there are a couple of questions. Who told you, who asked you to compute the arithmetic mean? That can be median, that can be mode, that can be geometric mean, that can be harmonic mean. So the question comes, which of them is a better measure, which of them is going to give us a better value of the population mean, which is unknown to us. That is not known to us, but we want to know only on the basis of this sample. So, what are the issues related with this type of problem? How to get this value, how to know whether the value is good or bad, etc. These are all the issues which are handled under the topic of estimation of parameters, and that is what we are going to start from today. Well, one thing I would like to make it clear before I come to my lecture formally, that in this estimation of parameter part, my main interest will be to let you know that how are you going to get a good value. Once you get the value, then you can easily compute it in the R software. So, the role of R software in this chapter may be comparatively less than other lectures, right. So, here we have to basically concentrate on the basic fundamentals. Once you are clear about the basic fundamentals, then estimating them on the basis of sample of data in the R software is not a difficult thing at all. That is my promise to you, and as soon as I come to the lecture, you will realize the same thing. So, now what I am going to do in this lecture, I will try to explain you the issues, the concepts, etc. related to the estimation of parameters. So, basically in this lecture, the amount of mathematics or the amount of algebra is going to be very less, but I will try to give you the basic ideas, right. So, let us begin our lecture and try to understand what is this estimation of parameters and what we really want to do. Okay, so, let us begin our lecture. Okay, so, now in this case, first we are trying to learn about what is the need for drawing statistical inference, and then we will try to discuss the smaller topic. So, we know that statistics deals with drawing conclusion from observed data from a sample, and these conclusions are drawn that are valid for sample or the entire population. That is my question mark. What do you want? Means the conclusion that you are getting on the basis of sample, will they, or do you want them to remain satisfied only for that sample, and as soon as the sample changes, the conclusions will change, or they should remain valid for any of the sample that you can draw from the population. So, the answer is the conclusion should be valid for the entire population. So, what we try to do, that we suitably try to draw a sample of observation from the population, or that is called as sampling from the population, and then we try to analyze the sampled items or sampled units, and we expect that we can draw the conclusions about the population as a whole. They are not remain valid, they will not remain valid only for the sample, but they will remain valid for the entire population, right. So, under this type of objective, the first question comes, whatever is your question, whatever you want to know, that has to be transformed or that has to be defined through a random variable, right. And whatever are the characteristics of that phenomena or the process from where you want to draw the inference or you want to know the answer of your question, the characteristic of that phenomena can be prescribed by a probability function. That can be a probability density function or a probability mass function, depending on the nature of the random variable. And then we have to think and decide that which of the statistical tool has to be used, so that you get a correct statistical outcome. And for that, depending on the tool, we need to have some basic assumptions which are to be satisfied while we are trying to collect the observation, and when we are trying to use this statistical tool over the collected observations. So, for that we will always have to make some basic assumptions, and this is a two-way process, that first you try to fix that what type of statistical tool is going to give you the correct outcome, and then you have to look into the need and requirement of the tool which are to be satisfied while collecting the data, and vice versa also, that while collecting the data you have certain characteristics. You try to see that these characteristics can be satisfied by which of the probability function, or what statistical assumptions you need so that these assumptions are, or these characteristics are satisfied in the probability function. Right. Now, for example, if the process has a tendency to produce the correlated observation, that means the concerned statistical tool and probability function should incorporate this feature through the properties of random variable. For example, up to now you assume in most of the cases that let x1, x2, xn be identically and independently distributed random variables. Now, you can choose the proper assumption that either they are only identical, only independent, or say none. Right. And if the required statistical tool are to be developed based on the assumption of the random observation with IID, that means identically and independently distributed observation, then the observation should also be collected such that they satisfy the requirement like to be random, identically and independently distributed. So, assumptions should be satisfied in the observations, and observations should also satisfy the assumptions. Okay. And in case if you try to deviate from any such assumption, there is going to be some violation, and as soon as there is any violation, then some errors, incorrectness or inefficiency in the statistical conclusion will be introduced. Something will happen. What will happen? It will be dependent on what type of assumption is getting violated under what type of circumstances. But in case if this happened, then we need to change the tool that we are trying to use and the methodology that we are trying to employ, and we have to choose the correct tool and correct methodology. And that is why there is a need for developing the appropriate statistical tool for the given data. As we have discussed in the lectures in the beginning, that only the correct tool on correct data will provide the meaningful, correct, efficient and correct statistical inferences. That we always have to keep in mind. Right. So, whenever we are trying to learn something about the population, that has to be done on the basis of a sample. That is the basic objective of statistics. Right. So, if the random variable x1, x2, xn are independent and identically distributed, then the random variables constitute a random sample of size n from the common distribution f. Right, because means you have done many such example, let x1, x2, xn be a random sample from normal population or normal distribution with mean mu and variance sigma square, or let x1, x2, xn be from exponential distribution with parameter lambda. So, we try to assume that these random variables are going to constitute a random sample of size n from a common distribution f, right. Means if you try to say that okay, the first observation is coming from normal, second is coming from Poisson, third is coming from binomial, fourth is coming from exponential, then I think the statistical process will become too complicated. So, we are trying to assume here that all the observations are coming from a common distribution, that can be a probability density function or that can be a probability mass function, right. So, this distribution is going to represent the distribution of the random variables in the population, and when we are trying to draw a sample from this population, then we expect that the sample observation will also have the same characteristic which are present in the population capital F. And this goes without saying, you will not find anywhere written, but it is assumed by default that the sample is always representative. As soon as you say this is a sample, that goes without saying that the sample is a representative, and representative in the sense that it is going to present all the characteristics which are present in the population, right. So, the meaning of the representative sample is that all the characteristics present in the population are also contained in the sample. Now, that is a different aspect, that how are you going to collect such observation, and there are several ways to get such representative samples. In fact, in statistics we have an area sampling theory, and there we try to learn about different types of sampling schemes, and they try to help us in taking a decision that how should we draw the random sample so that it is representative. And in case if the sample is not representative, then the statistical inferences may have some type of error, bias, discrepancy, etc. So, that is why we always assume that the sample must be representative sample of the population, and this is going to avoid any type of discrepancy or say bias in the estimation or forecasting of the parameters. Right. Now, in many applications you will find that the population distribution function f is unknown to us, and that is unspecified. We do not know what is the form, like as we do not know whether it is normal or say Poisson. We do not know what are the values of the parameter, like as mu sigma square in case of normal distribution or say lambda in the case of Poisson distribution. So, what we have to do? We try to use the data to make such inferences about f, right. And whatever is my population, that is going to be described by the distribution f, and distribution f is going to be specified by the parameters. But there are two options that sometime the f can be prescribed through the parameters and sometime it can be prescribed without parameters. So, based on this criteria, we have two types of statistical inferences, or we have two types of setups which help us in dealing such problems, and they are called as parametric and non-parametric inferences. So, the setup in which the form of the underlying distribution is known, right, through its parameters. That means, we know that it is a normal population and its mean is this, variance is this. Then it is called a parametric setup. That means, you have information about the form and the parameters, and whatever statistical inferences we try to draw from such setup, they are called as parametric inferences. Right. For example, if I say that f is normal distribution function having an unknown mean and say variance, the variance can be known, that can be unknown, it depends on different type of conditions. Or I can also say that f is a Poisson distribution function whose mean is unknown to us, that means lambda is unknown to us, right. And on the other way, the setup in which the form of the underlying distribution is unknown and it is free from parameters, it is called as non-parametric setup, and in such a case the inferences are drawn using this setup, and those type of inferences are called as non-parametric inference, right. And in statistics you will see that we have an entire area of this parametric inference and non-parametric inference. In this lecture and in this course, we are going to talk only about the parametric inference, right. So, now the statistical methods are used to make decision and draw conclusion about the population, and this aspect of statistics, this is generally called as statistical inference, right. There are certain statistical techniques which utilize the information in the sample, and they help us that how should we draw the statistical conclusions in the correct way, right. So, what is really going to happen? The framework of statistical inference allows us to infer from the sample data, and our conclusions are going to be about the population of interest, and this is obtained at a given pre-specified uncertainty level and knowledge about the random process which is generating the data. Well, you have to understand that you are trying to know about a very big population on the basis of a very small sample of data, and every time you try to draw the sample from the population, there can be different sample. The probability of getting the same sample is very less, which you have seen in many applications wherever I was trying to generate the random numbers from the R software in a specified probability mass function or probability density function. You have seen that every time you are getting a different sample, and those values are trying to give a different value of the statistic that you are trying to compute to draw statistical inferences. So, certainly there is going to be uncertainty involved in the statistical inferences, and since we really do not know with 100% confidence that what is the exact form of the distribution function f, so we try to assume an appropriate form, but there may be some discrepancy between the true form and the form that we are going to consider. So, the uncertainties from such factors will be reflected in the process when we are trying to take conclusions, right. Now, as an example of a parameter estimation problem, suppose that an experiment is conducted to know the efficacy of the medicine in controlling the body temperature, that is fever. The medicine is administered to a group of patients and its effect is recorded by measuring the time of control of fever, right. Now, in case if you try to take a group of people and they are given the medicine, some persons may have the body temperature control up to say this 5 hours only. Some people may have the body temperature control for more than 5 hours. Somebody may have 6 hours, somebody may have 7 hours, somebody may have 5.5 hours and so on. So, you will see that these values have certain amount of variability. So, this variability is naturally going to be present between the individual patients, and this variability can enter into the data because of several reasons, like as the age of patients, body structure, body weights, etc. Right. So, that can happen. So, now our objective is to estimate the average time or the mean time to control the body temperature based on the sample of data to compute a number that in some sense a reasonable value or a good guess of the true parameter mean. For example, you have seen that many times we say that whenever a person has a body temperature or fever, the doctor says, okay, try to take the medicine after every 8 hours. How does this doctor comes know that the medicine has to be given for 8 hours? Because the experiment was conducted and it was found that once the dose of the medicine is given to a patient, on an average this can control the body temperature up to 8 hours. So, the doctor does not know what is your body structure inside your body, but after having a lot of experience, he can say that okay, whatever be the body structure, this medicine is going to work approximately at 7 to 8 hours. Right. So, sometime you can see the body temperature remains controlled for 7.5 hours, then 8 hours and 9 hours, or even sometimes more than this. Right. So, that is what we mean by saying that we are trying to estimate only the average value, and the number what we are finding, this is called as a point estimate. Have you ever observed that the doctor says, okay, this medicine can control the body temperature for 6 hours or for 8 hours, or the time that you are going to take from your home to college is about 20 minutes. So, you are trying to specify a value which is a point. So, that is why this type of estimation or this type of statistical inferences, they fall under the purview of point estimate, and we want to have the procedure for developing such point estimates of the parameter that have good statistical property. Good statistical property means, for example, if the doctor says to the patient that your body temperature will remain in control for say 8 hours, and then the patient asks, okay, will this be 7 hours 30 minutes or say 8 hours 30 minutes? And if the doctor says no, that can be any duration between 2 hours to 20 hours. Do you think that is it a very efficient statement? So, that means the way it is computed, that is not a good way. So, we always want to have a value of the estimate with some good statistical properties. What are those good statistical properties? That I will start discussing one by one from the next lecture. And he will also be able to establish the precision of the point estimate, that how good it is, what is the variability about this value, right. So, in case if you want to draw such statistical inferences, so it is necessary to make some assumption about the relationship between the sample and population, so that the sample data is used to make inference about the entire population. And one such a basic assumption is that there is an underlying probability distribution that is going to represent the population, and this probability distribution is such that the measurable values of the items in the population can be thought of as being represented by the random variable having this distribution. So, for example, if you want to measure the height of some students, so you say that my random variable is going to be height, and you have to specify that okay, the distribution of the heights in the student population is, for example, going to follow a normal distribution with some mean and some variance. So, this type of assumption is needed. So, the primary goal in a statistical inference is to find a good estimate of the population parameter, and if there are more than one parameters, we have to take care of them also, right. And these parameters are associated with the probability distribution, which is believed to characterize the population. For example, if I say we are assuming that my population is normal, then there are going to be two parameters mu and sigma square, which are going to characterize the normal distribution. And if these parameters are known to us, then one can characterize the entire population. For example, you know that if you know the value of mu and sigma square in the normal mu sigma square distribution, then you can find out its mean, variance, skewness, kurtosis, curve, etc., whatever you want. But what's really happening in practice? That these parameters are unknown to us. So, one of the very important objective is to first estimate them, right. And one can attempt to obtain these estimates as a function of the sample values, that the value of the parameter has to be known on the basis of observation that you have collected, and the values of these parameters can be obtained at a point as well as in the form of an interval, right. So, when the values of the parameters are obtained at a point, the estimation procedure is called as point estimation, and when the values of parameters are obtained in the form of an interval, the estimation procedure is called as an interval estimation. For example, means if I ask you a very simple question that how much time do you take from your home to college? Now, you have two options. You tell me that I take 20 minutes. That means you are trying to tell me the value of the time at a point, and this is going to be the point estimate. But you can also tell me, okay, I will take say between 15 minutes to 25 minutes. So, that means you are trying to specify the time in the form of an interval 15 to 25. So, this is called as an interval estimation, and when you are trying to give me only here a value, say 20 minutes, then it is called as a point estimation. But the question is this, when you are trying to find out these values 20 minutes or 15 minutes or 25 minutes, how are you going to obtain them? They have to be obtained on the basis of given sample of data, but where you have to employ the data? The question is what you really have to compute, what you really have to calculate, so that you get these values which are representing the truth. So, the question now here is, what does this function look like, and if there is suppose more than one such function, then what to do? For example, if you want to find out the average value, and suppose you have two options, you can compute the arithmetic mean, or you can compute the say this median, mode, harmonic mean, geometric mean, then which of them has to be utilized, and which of them is going to give you the correct value or more precise value? That is the question, right. So, the next question is, what is the best approach to estimate the population parameter on the basis of a given sample of data? And the answer is given by various statistical concepts such as bias, variability, consistency, efficiency, sufficiency, and completeness of the estimates, right. And that is what we are now going to study in this chapter in the forthcoming lectures. So, what we are going to assume? That we are going to assume that there is a sample of observations, and this sample is a random sample which has been drawn from the population of interest, and the sample values are going to be indicated by say x1, x2, xn, where x1, x2, xn are written in the lowercase alphabet, that is small x, like this one, small x1, small x2, small xn, right. And sometime just in order to make the representation clear, we will simply write here as a x, right. So, my random variable here is going to be capital X, and these values are going to represent the realized values of this random variable x, right. So, it can be said that this x1, x2, xn, they are the small number of observations which are collected on the random variable x. For example, if x is your here height, so what you try to do? That you try to suppose to take a sample of 20 students from your class out of say this 100 students, and you try to find out their values of heights. So, there are going to be 20 values of height. So, this can be written as say x1, x2 up to here x20. So, this is what we mean when we are trying to say that let small x1, small x2, small xn are the say this an observation which are collected on this random variable x, and this capital X is going to follow a certain distribution. Now, definitely when you want to estimate a population parameter, then you need to do all the calculations only on the basis of the random values or the random sample that you have obtained. So, in statistics there is a general say this understanding, or there is an understanding that with Greek alphabets we try to represent the parameters, right. So, usually you will see that mu, sigma square, lambda, they are representing the parameters. So, in general we will assume that now we have a parameter theta which is unknown to us, and theta can be a scalar quantity or this can be a vector quantity, and this theta is unknown to us. So, we want to know its value on the basis of the random sample, or that the value what we have obtained. So, obviously means we are looking forward to find out the form of a function that can give us the appropriate value of the theta. So, definitely this function is going to be a function of the random variable. So, the function of the random variable is called as a statistics. So, now we can assume that we are going to consider a statistics T x which is used to estimate the population parameter theta, and theta can be a scalar as well as a vector. And once we are trying to do it, we say in a statistical language that T x is an estimator of theta. So, T x is always going to be random variable, that is a statistic which is a function of random variable, right. And now what will happen? Now you will try to calculate the value of T x, calculate T x for given data. So, now what will happen? This will give us a value here like as here T say small x, right. So, that will be the value of that capital T x. So, now in case if you want to indicate that this unknown parameter theta is going to be estimated by the statistics T x, then we try to write it like here like this. We will write down the parameter here theta, that is equal to here T x, but definitely this is a wrong statement that theta is equal to T x, because theta is a known value which is based on the population, and T x is the value that is based on the sample. So, what we try to do? We try to put here a hat like this, and this is called here as say theta hat. So, as soon as you try to put a hat on the parameter, that is going to indicate that this value has to be obtained on the basis of given sample of data. So, theta is unknown, but theta hat is going to be known, and this is going to be known based on sample values. This is what you have to keep in mind. And yeah, means I am taking here the symbol hat, but many times we can also use other symbols also like as tilde or double bar or double tilde and so on. So, well, I am simply trying to say that we try to put a symbol on the upper side of the parameter to indicate that this is going to be an estimator, right. And when we try to calculate the value of t on the basis of given sample of data, we try to write this T x now as say here T small x, because small x is the observed data that is indicating this one. So, this T x is a random variable, but this capital T is small x, this is observed value, and this is dependent on the actual sample, that whatever sample you are trying to draw, this value is going to be changed, and if you try to change the sample, this value is going to be changed. For example, if I say that capital T x is equal to 1 upon n summation I goes from 1 to n capital X I, which is based on a sample say here x1, x2, here xn. So, this is going to be a statistic, this is going to be a random value, and this is an estimator and of some parameter. But when we are trying to observe the values of this random variable, that means we are trying to observe a sample of data, then we try to compute this capital T capital X, that is the statistics, and the value of this capital T x here is obtained here as a T small x, which is 1 upon n summation I goes from 1 to n small x I. So, small x I is the observed data, right. So, this x1, x2, xn, they are the realized sample. and whatever is the value, that is going to be a numerical value. That is what you have to keep in mind, right. Because estimator is a random variable and estimate is its numerical value, which is based on the given sample of data, and in case if you try to change the random sample, these numerical values are expected to be changed and this value of the statistics will also change, right. So, since the sample values are realization from a random variable, so each sample will give us a different value of the estimate of the population parameter. Now, the question is this, whether this population parameter is going to be a fixed value or a random variable. So, we are going to assume in this course that population parameters is a fixed value, that is our assumption, but it does not mean that parameters always has to be only fixed. The parameters can also be assumed to be random. For example, when we are trying to deal with Bayesian statistics, where we assume the parameter theta, this has got some PDF or say probability mass function, right. So, yeah, so both the options are possible, but once again remember one thing, that in this course we are assuming that the parameters are fixed. Okay. Now, when we are trying to obtain the value of the estimator, then several question comes up. That the first question is how are you going to obtain a form of the statistics, so that you come to know that you need to find out summation xi or say summation xi square. So, that is the approach, and these are and there are some estimation techniques which will help us. Once you obtain the values from those estimation methodologies, then the question comes how to judge whether the obtained values are good or bad. So, now from the next lecture I will try to handle all these issues one by one. So, there are several properties of the estimators which we expect that if those properties are there, then we can say that the estimator is good. So, these properties are unbiased estimator, efficient estimator, consistency, sufficiency, completeness, etc., beside a couple of others. So, we are going to talk about these properties in the from the next lecture, but one thing you have to keep in mind. Now, suppose I have to teach you all these properties. I cannot teach all of them at the same time, right. I have to take up one by one. So, in most of the books you will see that they are handled that first they try to explain about the property of unbiasedness, then efficiency, then consistency, then sufficiency, and then completeness. So, sometimes people try to take it that this is the order of importance. So, here I would like to mention very clearly that this is not the order of importance. These are different characteristics, and having one property does not necessarily imply that other properties are also satisfied. There is no ordering among these properties, right. Okay. So, now we come to an end to this lecture, and well, that was only a storytelling type lecture, but it was very important for you to understand that what are we going to do now, what is our objective. And many times I have seen that the terminologies like estimator, estimate, etc., what is here hat, that creates a big confusion among the students. So, you please try to revise this lecture, and I have intentionally not given you any mathematical theories or details in this lecture. Now, you have understood what are we really going to do. Once you know this thing, after that the life becomes simpler, right, and you can understand the topics that one by one they are going to come, and then you have to learn, but when you are trying to employ them, you have to use all of them together. Right. For example, when you are going to obtain a statistics to estimate a parameter, you have to test whether this is unbiased, whether this is consistent, whether it is having the property of sufficiency, completeness, etc. So, you try to revise this lecture, and then I will see you in the next lecture, and I will try to handle one property at a time, but without any ordering. So, you practice, and I will see you in the next lecture. Till then, goodbye.